Exponential growth and decay. So let's look at an example. In 1990, Florida's population was 13 million. Since 1990, the state's population has grown 1.7% each year. Florida's population is growing exponentially. To find Florida's population in 91, multiply the 1990 population by 1.7% and add this to the 1990 population. So 1991 is 1.7% plus the 100% of the 1990 population, or a combined 101.7% of the 1990 population. So here's a function that models for exponential growth since 1990. We could use y equals 13.0 for our 13 million we started with, times 1.017 to the x. So 13 is our population in millions that we started with. 1.017 is our 101.7% as a decimal. And our x would be the number of years since 1990. So in exponential growth, we can model using the formula y equals a times b to the x. A has to be greater than 0. And b, because we have a growth rate here, the b value has to be greater than 1. So we have a base greater than 1. So the a is our starting amount. Our b, the base, which is greater than 1, is the growth factor. And the x will be the number of cycles or number of frequencies that this growth rate has occurred. So let's look at some more real-world examples. We have, since 1985, the daily cost of patient care in community hospitals in the U.S. has increased by 8.1% per year. In 1985, such hospital costs were an average of $460 per day. So we're looking at relating this to y equals a times b to the x to write an exponential model of the cost of hospital care. So we're looking for values. The a is going to be where we started, and we're starting at $460 per day. The b value is going to be this 8.1%, but we're also including the previous amount we started with. It's 8.1% on top of the $460 per day. So we're going to have to take 100% and add that 8.1% for growth. The x will be our number of years since 1985. And the y is going to be the cost that comes out, would be the cost of community care at various times. So we're going to put x will be the number of years since 1985. The y coming out of the equation is our cost of care after 1985 for each year amount. A is the initial cost in 1985. So the a value, or our beginning amount, is the $460. The most important thing to pay attention, though, here is the growth factor. The growth factor at 8.1% is added to the 100% because we still have all the previous 100% of cost. We have the 8.1% in additional, or 108.1%. So we use 1.081 as our growth rate, which gives us the exponential function, y equals 460 times 1.081 to the x. And then we could use that to find cost in years after 1985. So let's say we want to use the equation to find the approximate cost per day in the year 2000. Well, how many years have passed between 1985 and 2000? Well, 15 years went by. So we're going to use 15 for our exponent. So I'm going to use my calculator, 1.081 to the 15th power times the 460 we started with. So the cost would be about $1,480 a day in the year 2000 for a stay in a community hospital. All right, you guys try this on your own. Suppose your community has 4,512 students this year. The student population is growing 2.5% each year. Write an equation to model the student population. So you guys pause the video here and see if you can write the exponential growth function for the board problem. All right, welcome back. So using our y equals a times b to the x, we have 4,512 is our beginning number. Our growth rate of 2.5%, we're going to use 1.025, and then x would be our number of years. So now take the formula that you made and find the student population in 3 years. Come back on pause. All right, welcome back. So if we put 3 in for the exponent, we would end up with 4,859 students. When we have a decimal there, but we're kind, we round to the nearest whole student. We don't deal with partial students. So we round that up to 4,859. All right, so far we've talked about exponential growth. Let's shift over and talk about exponential decay. And it's very much like exponential growth, except the base for decay has to be a number between 0 and 1. So growth had to be a number greater than 1. We can't use 1 itself because 1 itself would cause linear growth, and we're talking about exponential growth or exponential decay. Decay means this b value has to be a number between 0 and 1. So everything else would look the same as growth except for the b value. The base, which is between 0 and 1, is the decay factor. So when a number is decreased by 5%, the result is 95% of the original number. So when you find decay factor, think of 100% minus the percent of decrease. So when we had exponential growth, we took our growth rate, we added it to 100%. With decay, we're going to start with 100% and subtract away the amount we're decreasing. So a 5% decrease, we want to use a growth factor of 0.95 or a decay factor of 0.95. So you guys try this one on your own, see if you can write the exponential function for decay. Since 1980, the number of gallons of whole milk each person in the U.S. drinks each year has decreased by 4.1% each year. In 1980, each person drank an average of 16.5 gallons of whole milk per year. Write an equation to model the gallons of whole milk drunk per person. You guys try to write the function and come back and we'll see how you did. All right, so our function, we're looking at x would be the number of years since 1980. Y, what's going to come out of our function, is the consumption of whole milk in gallons. The a value is going to be 16.5. That's the initial number of gallons in 1980. And our decay factor, this is the hard part we're looking at. Focus in on this. We have 100% minus the 4.1%. So we're going to use 95.9% or 0.959 as a decimal. So with decay or decreasing, we're looking at 100% minus that 4.1 to come up with 0.959. And our function looks like this. Y equals 16.5 times 0.959 to the x. Now, use your newly created exponential decay function to approximate consumption per person of whole milk in the year 2000. All right, so in the year 2000, from 1980 to 2000, we have had 20 years go by, so we're going to use our exponent of 20. So to put in your calculator, 0.959 to the 20th power times 16.5, and we get that the average consumption per person around just over 7 gallons per person. Hope that helps you guys get going on exponential growth and decay. Have a great day. OUT spells out.